Hello. After covering the energy storing elements, inductors and capacitors, now we will learn how to analyze circuits which contain these elements. We will start with first order circuits which only have one inductor or one capacitor. After making basic definitions on first order circuits, we will analyze the response of first order circuits to constant inputs. We will specifically cover what is the natural and forced responses and also how to measure time constant. At the end of this lecture, we will do a bunch of exercises for first order circuits. The constituent relationships for inductors and capacitances are mathematically written using integrals and derivatives. Therefore, we will use differential equations to describe the circuits that contain capacitors and inductors. The order of the differential equation will be usually equal to the number of irreducible capacitors plus the number of irreducible inductors in the circuit. Circuits that contain only one inductor and no capacitors, or one capacitor and no inductor, will be represented using a first order differential equation and therefore will be called first order circuit. Let us remember what was the order of a differential equation. Imagine we have a differential equation in the form of y double dot plus 3y dot plus 5y is equal to sine t. This is a second order differential equation because y double dot is the highest order term and it is the second derivative. If we would have third order derivative like y triple dot, then this would have been a third order circuit. Previously, we learned very powerful circuit analysis tools, namely Thevenin and Norton equivalent circuits. In Thevenin equivalent circuits, we can reduce a circuit to a single voltage source and a series resistor, and from the output ports of this part of the circuit, this will be equivalent to the previous circuit. Now we will use these equivalent circuits for the solution of the first order circuits. Specifically, we represent on one side the Thevenin equivalent circuit. On the other side, we have the energy storing element. And if we have a capacitor, we have the Thevenin equivalent circuit and the capacitor. If we have an inductor, we have the Norton equivalent circuit and an inductor. All of the first order circuits can be represented using these two topologies and can be then analyzed easily. Let us first look at this first order circuit to make some important definitions. Firstly, the input Vs to this circuit is A times cosine 1000t plus theta. So the system has a sinusoidal input. At steady state, we would expect it to have a sinusoidal output. Then the output voltage of the circuit is the voltage over the capacitor Vt here. Before t is equal to 0, the circuit is at steady state, but at t0, this switch closes, effectively bypassing this R2, and this disturbs the circuit, and this will cause a transient response. Indeed, here we see the circuit behaving in steady state, always doing the same response. And at t is equal to 0, we have the switch closing and the circuit makes a transient response, and afterwards it settles to another steady state which is another sinusoidal, but now with a different amplitude and possibly phase. If the input to a first order circuit is sinusoidal, then the steady state response of that circuit will be sinusoidal as well. This is one of the great properties of linear systems. Before the switch is closed, the system is at steady state, and the output, the voltage over the capacitor, can be expressed as Vt is equal to B times cosine 1000t plus phi for t less than or equal to 0. From this expression, we can calculate the initial condition at V is equal to 0 as V times cosine phi, which we will use to solve the circuit for t greater than 0. Indeed, this initial condition gives us the energy stored in the circuit at the beginning of the second interval. After the switch closes, the response will have two parts, the transient response and steady-state response. If the circuit is stable, the transient part will be a first-order exponential decay and it will die out. Steady-state part will have the same functional form as the input and it is also called the forced response. So therefore, we write complete response of the circuit is equal to transient response plus steady-state response, or we can write this as complete response of the system is equal to natural response, basically the response of the circuit because of the initial conditions, plus the forced response, the response of the system because of the forced input to the system, which is the voltage source. We will learn how to derive this mathematical expression, but for the time being, please note that the natural response or the transient response of the system goes to 0 as t goes to infinity, and at steady state we only have the response of the system for the forced response, in other words, due to the input. The natural response is the general solution of the differential equation when the input is equal to 0. The forced response is a particular solution of the differential equation for the specific input to the circuit, for instance here the sinusoidal input. Natural response is in the form of an exponential for a first order circuit, k times e to the minus t0 divided by tau. If we set the initial time t0 is equal to 0, this just takes this form. The constant k depends on the initial condition, the capacitor voltage or inductor current in the circuit, which also determine the initial energy stored in this circuit as well. We will cover three special cases for the forced response of the first order circuits. Specifically, the voltage input is a constant of the form V0. The input is an exponential of the form V0 times e to the minus t over tau, or a sinusoidal of the form V0 times cosine omega t plus theta, and we will learn how to derive the response of the system for these three inputs. So how will we solve first order circuits? We actually have a very simple procedure which we should follow all the time. Firstly, as step 1, we find the forced response of the circuit before the disturbance, and we use that forced response in order to find the initial condition of the circuit. In other words, the energy stored in that circuit at t is equal to t0. Afterwards, we find the forced response of the system after t0, after the disturbance of the circuit, and we add to this the natural response of the circuit, and we use the initial conditions to find the parameters of the natural response. Now we will get the differential equation governing the dynamics of this circuit. And we observe that this is a first order circuit because the circuit contains only one capacitor. In this circuit, the disturbance to the circuit comes in the form of the closure of this switch at t is equal to 0. When this switch is closed, effectively the resistance 1 gets bypassed, and the circuit consists of then a voltage source, resistor 2, resistor 3, and the capacitance. So what do we do as the first step? Since we need to get Thevenin equivalent circuit of this with respect to the ports which are connected to the capacitor, we need to find the V open circuit and R Thevenin. R Thevenin can be very easily found by taking the parallel resistance of R2 and R3. Note that R1 is bypassed and it's not a part of the circuit anymore. And RT is equal to R2 times R3 divided by R2 plus R3. And the V open circuit for this circuit can be found by the voltage divider rule. V open circuit will be equal to R3 times the total resistance of the circuit, R2 plus R3, times the input voltage Vs. And this will be our V open circuit. Accordingly, the whole circuit reduces itself to the simple form in which there is a voltage source, a Thevenin resistance, and the capacitor. For this equivalent circuit, I can easily write the Kirchhoff's voltage law. The open circuit will be equal to RT times IT plus VT. The VT is the voltage over this capacitor. However, here the problem is that I don't know what is IT. I can write IT by using the constituent relation of the capacitor. IT is equal to C times dV over dt. If I plug in this expression for I in this equation, I end up with my first order differential equation. dV over dt plus V over RT times C. RT times C will be the time constant of the circuit, is equal to a constant V open circuit divided by the same expression RT times C, which is the time constant. In case I have an inductor instead of a capacitor in the circuit, I can do the same procedure. However, this time I will need to find the Norton equivalent circuit, which reduces the resistor network part of the circuit to a single current source and to a single equivalent resistor. And RT is the same as the Thevenin resistance for the Norton equivalent circuit as well. And I short circuit can be simply found by V open circuit divided by R Thevenin. And in this circuit, the inductor voltage will be given by V is equal to L times di over dt, the constituent relation for this circuit. And applying KCL to this circuit, we just have I short circuit is equal to V over R plus IT. And by using the constituent relationship for V, we can write this as this expression. And all of this reduces itself to a differential equation which is first order and which has the exactly same form of the previous differential equation we have found for the circuit with a single capacitor. Here the only difference is we write this equation with currents instead of voltages. And secondly, the time constant have a different form. It is here RT over L instead of RT times C. Here is my differential equation for first order capacitor circuit, and here is my equation for the first order inductor circuit. And as you can see, they have both the same form. dx over dt plus x over tau is equal to the constant k. Let's try to solve this equation. Firstly, I take the differential part to the left side and all the rest to the right side. And I separate then the variables such that I just have x's on one side and other variables on the other side. And afterwards, I simply take the indefinite integrals of these both sides. And when I take these indefinite integrals, I should also add here a constant for integration in the form of this d. Remember, the integral for 1 over x dx is equal to ln x. And since I have this, I can just do the same integration for this term, and I end up with ln x minus k tau. And for the right side, I have the integral of 1 times dt, and therefore this side will become minus t over tau plus the integration constant. If I solve this expression by taking the exponent of both sides, I end up with xt minus k tau is equal to e to the minus t over tau plus d. And I can take the expression kt to the right side and I end up with this expression here. Now, here I can change this expression to a more convenient form by defining a is equal to e to the power of d, and I can write it as k tau plus a times e to the minus t over tau. Now, here I have a problem. I need to find one way or other what is the value of A. In order to do this, I will utilize the initial condition of the circuit. If I plug into this expression t is equal to 0, that expression becomes k times tau, that's a constant, plus a times e to the power of 0. E to the power of 0 is equal to 1. Therefore, a is equal to x0 minus k times tau. Using the expression for a, I can write it into this expression, and then I end up with the final expression here, which just shows me the final solution for my first order differential equation. Xt is equal to k times tau plus x0 minus k tau times the exponential decay term in the form of e to the minus t over tau. But this was for a circuit at which we just had a constant input to the circuit in the form of Vs. Again, let's remember this is our first order RC circuit. This is our circuit's first order in the general form, and here I have my first order RL circuit with the inductor. Since the solution for the first order general form is given here, I can substitute instead of K, the open circuit divided by RT times C, and for tau, RT times C, and find the general output form of the first order RC circuit, which is Vt is equal to V open circuit plus, in parentheses, V0, the initial condition, minus V open circuit times e to the minus t over tau, the time constant, which is in this case RT times C. And when I look at this, I realize that the term which is on the right with the exponential decay will converge to 0 as time goes to infinity. Therefore, V infinity will be equal to V open circuit for a stable circuit. Capacitance in a DC circuit, therefore, behaves as an open circuit in the steady state. If I do the same variable substitutions for the first order RL circuit by writing K is equal to RT over L times I short circuit and tau is equal to L over RT, I end up with this expression for the solution of my circuit. IT is equal to I short circuit plus, in parentheses, the initial condition I0 minus I short circuit times e to the minus RT over L times T. And since this exponential term will again converge to 0 as t goes to infinity, in the end the current will be equal to I short circuit at t is equal to infinity, and therefore we can state that the inductor in a DC circuit behaves as a short circuit in the steady state. How can I find the time constant of a circuit if I don't know what type of elements are inside? Actually, I can apply some type of DC voltage, look at the output waveform in the oscilloscope, and find the time constant of the circuit. How? Remember, x infinity will be equal to k times tau, and xt is equal to x infinity plus this term. If I take the derivative of both sides, I end up with d over dt xt is equal to this expression here. So I simply took the derivatives, and as you can see, this constant term disappeared, and I took the derivative of e to the minus t over tau as minus 1 over tau times e to the minus t over tau, the same expression, and I multiplied it with this constant, which does not have any depending terms on time. Then if I evaluate this expression at 0, here on the left side I have the slope of my variable x at t is equal to 0, and on the right side I have minus 1 over tau times x0 minus x infinity. Since I know the initial value of the circuit, And since I know what the circuit value becomes after enough time passes, which I can look in my oscilloscope screen, I can solve this expression for tau, the time constant of the circuit, which is, for instance, R times C for the capacitor circuit. And I find this expression, x infinity minus x0 divided by the slope of the circuit at t is equal to 0. It is very easy to find tau graphically if I have the response of the circuit, which I can get from the oscilloscope. And at t is equal to 0, I find the tangent line to the variable of interest. Then I find the intersection of that with x infinity, and this point determines the value of my time constant tau. What is the value of the capacitor voltage 50 milliseconds after the switch opens? So in order to solve this question, we will use this equation. However, in order to use this equation, we need to find the initial voltage over this capacitor and the open circuit and also the R Thevenin. So let's try to solve this together. Before t is equal to 0, the circuit is plus minus 8 volts, 10 kilo ohms, the capacitor 2 microfarad, and this is directly connected to plus minus 2 volt voltage source. So when we look at this circuit before t less than or equal to 0, we realize that the 2 volt source is in parallel to the 2 microfarad capacitor, and considering that the circuit is at steady state, we can write that V0 is equal to 2 volts. When t is greater than 0 seconds, then the circuit will reduce itself to an 8 volt source, 10 kilo ohm resistor, and simply the 2 microfarad capacitor, over which we will have the voltage T. So this is equivalent to the Thevenin equivalent circuit, with the open circuit is equal to 8 volts and R Thevenin is equal to 10 kilo ohms. So I have right now everything in order to solve this question. Accordingly, Vt is equal to V infinity will be the open circuit voltage, 8 minus V0 minus V infinity, 2 minus 8, plus times e to the minus t over RT is 10 kilo ohms and C is equal to 2 microfarads. So if I multiply 10 kilo ohms with 2 microfarads, I will get 20 milliseconds. So accordingly, Vt will be equal to 8 minus 6 times e to the minus t over 20 milliseconds. Now I need to find the value of the voltage at 50 milliseconds. I will use the help of MATLAB for doing this. You can use your scientific calculators. 8 minus 6 times e to the minus 50 over 20, which is equal to 8 minus 6 times e to the minus 2.5, and this is also equal to 7.5 volts. So basically the value of the voltage will increase from 2 volts to 7.5 volts in 50 milliseconds after the switch opens. How long will it take for the inductor current to reach 2 milliamperes after the switch closes? This is indeed easy because this part of the circuit is indeed in Norton equivalent form, a single current source and a parallel resistor, and we have a single inductor here. Before t is equal to 0, before the switch closes, the current passing through this inductor will be equal to 0. And let us right now write the terms into this general form of equation. I of t will be equal to, I infinity will be equal to I short circuit, which is 4 milliamperes, plus I0. I0 is equal to 0. Then I will have minus 4 milliamperes again, times e to the minus RT over L times T. RT is equal to 1000 ohms. L is equal to 5 millihenries. And from here I will find also the tau value. So I can write this expression as e to the minus t over tau, and from here tau is equal to L over RT. L is equal to 5 millihenries and RT is equal to 1000, so this will be equal to 5 microseconds. That's the time constant. Accordingly, I of t will be equal to 4 milliamperes minus 4 milliamperes times e to the minus t over 5 microseconds. Now I need to figure out t when this becomes 2 milliamperes. 2 milliamperes is equal to 4 milliampere minus 4 milliamperes times e to the minus t over 5 microseconds. Let's solve this. I end up with 0.5 is equal to e to the minus t over 5 microseconds. Yes. And if I take the logarithm of both sides, I have ln 0.5 is equal to minus t over 5 microseconds. From here, I find t is equal to 5 microseconds with a minus sign times ln 0.5, and accordingly this is 3.47 microseconds. Namely, after the switch closes in just 3.47 microseconds, the current will reach 2 milliamperes. The circuit is in steady state before the switch closes at time t is equal to 0. Find the inductor current for t greater than 0. Now, when I look at this circuit, what I observe is before the switch closes, the inductor is in steady state, behaving like a short circuit. And the equivalent circuit for t less than 0 will be equal to plus minus 12 volts here, 100 ohms, 200 ohms, a short circuit and current I flowing through that, and the circuit is closed. Accordingly, I will be equal to 12 volts divided by 300 ohms, which is equal to, if I am not wrong, 40 milliamperes. This will be I0 as well, because the current over an inductor cannot change instantaneously. Inductor is an element with a memory. Inductor is an energy storing element. Now I need to go and draw the equivalent circuit for the t greater than 0. However, here I have an inductor, therefore I need a Norton equivalent circuit. I will have 12 volts here and 200 ohms there, so the source transformation will give 12 volts over 200 ohms, 60 milliamperes, in parallel with 200 ohms, and in parallel to these, my inductor, which has the 5 millihenry value. Now, I infinity, which is equal to I short circuit, will be equal to 60 milliamperes. Accordingly, I can write my I of t is equal to I infinity 60 milliamperes plus I0 40 minus 60 milliamperes, so in a sense minus 20 milliamperes, times e to the t over tau. What will be tau? Tau will be equal to L over RT, and tau will be therefore equal to 5 millihenries divided by 200 ohms, and accordingly tau will be equal to 25 microseconds. Therefore, I can write this expression as I of t is equal to 60 milliamperes minus 20 milliamperes times e to the minus t over 25 microseconds. This is my final expression for this question.